Thank you. So I'm one of the few that is not going to present with Reveal. I've got Slack for a corporation, and we do everything by PowerPoint. Um, but at least you'll get to see the big splash of cat yellow there. And the funny part about this template is you can see our secret for our autonomy up there. It's just a simple fraction. 2 to the fifth, 7 squared over 4/3. No, but in all seriousness, I'm here to talk about finding driving style patterns in machine data. So first, the background, orient you about our company. So we are one of the bigger manufacturers in Illinois, at least in the downstate part of Illinois. We're headquartered in Peoria, Illinois. We've got facilities in Aurora, Decatur, Peoria, Mossville, and we actually are opening a analytics office right here in Chicago. But you may know of us as a big industrial company. We make very big industrial machines, and we use machine differently than machine learning. This is a real machine, right? Large mining trucks, articulated trucks, excavators, motor graders. We have a very vast product line. We're actually into mining as well. We have rope shovels, hydraulic mining shovels, underground mining, and very diverse portfolio of products. But what they all have in common is they use mechanical, electrical, hydraulic systems to drive the machine around, to move the implements, to do work, to haul dirt, to dig, to dump, and all that's done by, for the most part, a diesel engine that produces torque, produces power, and the power is converted into moving the machine around. So what I show here is what my talk today is about. It's called the Integrated Powertrain System, or IPS for short. And the integrated powertrain system is a very complicated architecture and mechanical system. It uses traditional mechanical things like direct drive or the gear shifting, like the converter drive. Uses an upper powertrain, a lower powertrain, and of course the engine itself. And this just doesn't happen automatically. It's all controlled by electronics. So we have embedded control software. The control software is constantly trying to optimize along a number of different variables, such like the operator is giving it inputs, like he wants to accelerate or decelerate. He wants to produce a lot of power to move dirt. He also wants to feel comfortable. He doesn't want to be rocking around in the cab. And then on the other hand, the company that is producing the machine does not want to spend money on fuel, so we're trying to economize on fuel. We're trying to burn the fuel cleanly so there's not emissions. So this is all done with electronics and software. Software is very complicated. It has maps that are trying to pick how much fuel mixture to use. They want to be economical at some point, but if you're too economical, you lose power. You can't do your work, can't move the dirt around. So for long periods of CAT's history, we had the electronics, we had the data flowing in our machines, and we weren't making use of it. So enter the new age of data and telematics. Maybe about 7 years ago, we started putting on data loggers on the machines that could log the data autonomously and produce or send it back through the cell network or Wi-Fi or satellite or whatever the machine happened to have. You got to remember, a lot of these machines are working in an area without an infrastructure, so there aren't, a place to plug in to just push your data back through the internet. We're creating that infrastructure, so it can be expensive. But we've started moving more and more data through these Wi-Fi, cell phone, and satellite technologies. Now, all that data is time series data. It can come back to Caterpillar. We can put it in a repository and make use of it. So what are we doing with it? Well, I have a video here I'm going to show, just if you'll permit me, just a 1-minute video. This was introduced this spring, and it's a new initiative that we have called the Age of Smart Iron. Oops. So, find my mouse.
Smart appliances, and smart homes. An age where connected devices are improving lives, revolutionizing work. From job sites to generators to machines of all sizes, this is the age where iron flexes its intelligence. machinery that enriches lives, powers businesses, and builds communities, is given the connectivity to be even safer, more efficient, and more productive. This is the age where our industry evolves, the age where job sites become their own networks, where entire fleets speak the same language, and where work gets done faster with fewer setbacks. This is the new era of smart, and CAT is built for it. Welcome to the age of smart iron.
Okay, so about 2 years ago, I started meeting with the integrated powertrain system, and they said we have this process by which we have a lot of field data. We have virtual simulation models that we can drive with field data. It's like playback data. You play the data through the model, and it will exercise the control software, and then they can find problems where it doesn't work real well. It doesn't optimize around fuel, productivity, and operator comfort. So when they make changes to the software, they'd like to just be able to go grab a set of data, run it through their model to show that it's validated, it's actually achieving what they want. The process, though, was not as optimal as they'd like it to be. They would go through the data that they had and manually select some cycles that they thought were representative of the field, but they never knew. I mean, are they just pulling out of a corner of that data set? Is it one thing that that operator does and no other operators do? So they said, we really want to find a way to go across canvas all of our data and pull out a few patterns, not a lot of them, but a few patterns that represent the field. And they had started to do this manually. It was way too time-consuming to find examples of things that were done very often. On the other hand, if you tried to reduce the data and do some kind of reduction scheme, like doing histograms of certain, what we call channels, which are the time series, that doesn't work because for powertrain systems, it really doesn't matter in what order things happen, in what gear, with what order you go through gears, whether you're accelerating or decelerating. So the time dependency matters, although those operations can be time dilated, they can be longer or shorter, and they can be time reordered. So I rephrased this problem of how do I use represented data to validate my software as how do I automatically find these time series at scale, these patterns. First thing I wanted to get a real clear idea on was, well, what kind of patterns are we talking about? And this was the explanation they gave me. Well, we're looking for predominant ones that are the type of patterns that happen in this data more often than not. And we can't actually use a very long pattern because we're going to drive our simulation software. Simulation is a converging solution. It takes a long time usually, so you can only take up to about 10 or 15 minutes. Otherwise, that runtime gets long. And of course, their patterns were based on the powertrain features that they were very interested in, like the gear shifts, the speeds, the accelerations, torques, duration of the operations, and so forth. But clearly, after we got into the discussion, I realized they weren't looking for exact waveform matches. They were not looking through the data. When does it follow this, this inclination and so forth, sine wave? They weren't looking for that. They were looking for specific aggregate features across the multivariate data, but not exact waveform matches. And just a side note, if you're looking for a way to do waveform matches, take a look at dynamic time warping and symbolic approximate aggregation. We actually started down that path and did it for another project, but for this one, it wasn't about waveform, it's about features. So how many patterns were they looking for? That was another thing I asked. You're looking for 100 or 5? And they said, well, probably, we don't really know. We like the data to tell us how many patterns are in there, but the best guess is there's maybe 10 or 20 different patterns that we care about. So let the data decide. This image I'm showing you here is the continuous data that was recorded, and we're breaking it up into those 10-minute patterns. And so it was kind of important that we realize you don't have to do a sliding window search, that you could segment the data into 10-minute segments, and each segment, even though it's artificial where it happens, across a wide enough data set, that doesn't matter. We'll just partition the data. So here's our approach. I'm going to go through this kind of in a business analyst level, and then I'll show you a little more of the code behind it. So we start at the top left. We have the data logger time series, and for a given machine model, we might have 50,000 hours, 80,000 hours, something of that nature. And we're going to take all this data and segment it into 10-minute windows. Then we're going to calculate specific features related to the powertrain system. And we need to scale those because the features are not all on the same magnitude. We don't want one feature to outweigh the others just based on the scale of it. Then we run principal component analysis, PCA, and I'll explain this later, but this is to reduce the dimensionality of the data. And then we want to limit that dimensionality to the critical dimensions that really represent the underlying structure. So we have a rule of thumb just to limit the dimensions to 80% of the data variability. Then we go through a loop where we do iterative clustering. We cluster from about 5 to 20, and that range is sort of user configurable, but that's what's worked for us. And each time that we cluster, we use k-means clustering. This is pretty basic data science. We're not using all that advanced algorithms. But for each one of those, we calculate a dissimilarity score, which is something that I invented. And apparently, there's a couple different ways you can find the optimal number of clusters. I haven't researched all of them, but there are some other methods I'd like to try in the future. So our dissimilarity score gives us a value, just a single value for that set of k clusters. And then we look at them from 5 to 20 and pick the optimal one. So once we know how many clusters was the optimal one, we can pull out those centroids and then use those to predict against the data that we have and draw 5 samples. And this could be 5, it could be 3, it could be 10. But enough samples that I can show the time series windows, the sessions, and say, here's some examples of each of those clusters. Maybe you can find some introspection of what makes them similar. So a little more detail on each of those steps. Feature engineering, what do we mean by going and calculating these specific powertrain system features? So I'm not going to show you the ones that we actually use. Those are sort of CAT proprietary, but this was based on a journal article in the Society of Automotive Engineering, SAE journal, really where we got a lot of the ideas of doing this. And this is the list of their features. And if you look through those, they're just aggregations on a specific entity, like the time spent at low speed or the time spent in that window related to maximum acceleration. So this was, the paper here was actually a classification problem. They were trying to train a model based on driving, highway driving versus city driving, and then see if they could accurately predict any given set of time series which that falls into. So different problem, but same idea that we can use features to do an unsupervised unsupervised learning application. So now we have all this data. And by the way, what I just showed you, the feature engineering and the calculating the features, that's the hardest part of this whole process. This huge amount of data, it takes by far 95% of the time to, or maybe more, to get all that data. But once you pull it all, that's reduced data. It's a nice rectangular data set, maybe 150 to 400,000 rows and 50 to 60 columns, which are your features, right? It's actually like think of it like a big Excel spreadsheet. So this fits in main memory very easily now that I've reduced it, but I'm not able to do the clustering I want across the many columns because clustering in high dimensions becomes problematic. We like to reduce those columns. So what we do is we use PCA transformation. This like this little illustration because it's a good way to get insight. PCA, if you've not heard about it, takes multi-dimensional data set. In this example, there's 3 dimensions, and it finds the first axes of greatest variance. It calls that your first component, and then it finds the next axis orthogonal to that, that's second greatest in variance, and it kind of does that until it's completed all the dimensions. So then you can choose to reduce or drop the dimensions of least variance, like they go from the 3D geometry to a flattened 2D geometry, but they're kind of retaining the structure of the data and getting rid of those higher dimensions. So we do that, but not from 3 to 2. We do it from like 50 to 60 dimensions down to as many as you can count on one hand. So again, that's sort of arbitrary, but the second plot here shows how we do that. It's this rule of thumb about the 80-20 rule. We say, how many principal components does it take to get to the 88% of your cumulative variability as determined by these eigenvalues? So for the example I'm showing here, we started with 54 components, and at the 8th component, we had 80% of the variability. So really all those other dimensions are just noise. We don't really care about them. We'll throw them away. Another way to think about what PCA does is you still have all your features. So this plot shows on the vertical axis all the features, and on the horizontal axis, these are the 8 principal components we've kept. But not every feature has the same importance. There's a weighting, there's a, what they call feature loading that transforms you from the original data space to the PCA data space. So one thing you can do is take these features and sort them by like a sum squared value across the row, because not just one coefficient in one column is the indication important. It's really across the whole columns. So you do that, and you kind of see I actually show only about half of the features here, but my eye shows me that the ones at the top have the biggest coefficients, the biggest importance. You get down far enough, and they're all getting to be near 0. So, you know, those lower features, if you're trying to get some insight into what the data space looks like, lower features don't have a big impact on clustering, but the features at the top of this list would. So this is, now we take this PCA transform, fewer dimension data set, and we do unsupervised learning on it. We're just using k-means clustering. There are some other algorithms we could be using. We went with the simplest. This shows you the output of just one of those k values, k equals 13. So what do we know at this point? Well, we know how many observations or how many 10-minute windows fall into each of the clusters, and they're not even. You can see here some are more, some are less, depending on your data set. And on the right, we can get some insight into where those clusters are being formed by doing pairwise plots of every principal component. So it's a little bit hard to see, but the first row there is the first principal component, second row is the second, and then the same thing on the x-axis. So you get cross plots there of one principal component to the other. It's hard when you get to many components, but when there's few, you can say, well, this region in the principal component space is cluster 1. This other region is cluster 2, so forth. And we'll need that when we look at windows. We actually looked at sampled time series, and we're going to try to figure out what are they actually telling us. So final step to being able to generate these samples is what is the optimal cluster number. So I came up with a very just simple statistical method by which we take, you can see in this plot down on the bottom left, we take every combination of clusters, so cluster 1 to 2, 1 to 3, 2 to 3, so forth, and we do a student T hypothesis test on the means of every principal component. What we're looking for is, the way I describe this is that, you know, you start with 5 clusters. The clusters are big, they grab a lot of data, there's a lot of variability in that data, and so it's possible that a cluster doesn't have enough specificity in it. You'd like to shrink the cluster until it's, you know, just around enough data that it's unique. And as you shrink those clusters and they become more and more, the borders press in on each other, and now it's very difficult at the edges of the clusters for those values to be unique. So I was telling myself that maybe there's this, you know, convex curve that there's a peak at. So by summing up all of the t-tests that passed divided by the total, we're looking for a number that's close to 1, or the greatest number. It doesn't really work out that way. When you do it on a set of data, you get this kind of noisy line, and what I show here, there's like 3 that are at the max. Cluster 9, which is 9 clusters, 13 clusters, and 16. So talking with the IPS team, I said, you know, which one do you want to go with here? And they said, well, fewer is probably better up to a certain point, because we have to run simulation on every one of these clusters you provide us. But too few, and then we don't know, we're not seeing enough of the detail. Those clusters might be too general. So we went for the middle. We picked 13. This is one of the weak parts of the process that we hope to improve. So here's the implementation, and we are using Python. This is PyData. So we'll start with the data storage and the files. And we use HDF5 files, which is a hierarchical data format. These files are great for our type of data. We don't have textual data. This is numeric. It's binary. It's very large. And what HDF5 does well is compress that data. They have a chunking compression algorithm. For our data, it saves 90% of the data on disk. and then it actually reads off a disk faster because you read the compressed chunk, and then your CPU, which is faster than disk, can decompress that in memory faster than you could read the raw data. So HDF5 is great. It also provides a hierarchical storage model, so we can actually store things at different places within the data, and it stores metadata along with the data. So we save things like units of the sensor values, the scaling values. We have what the software part number might have been at the time the data was recorded. So if you wanted to do this don't ever use CSV for this kind of data. I mean, it would just be huge, and it wouldn't be able to store the data as efficiently. By the way, HDF Group is the nonprofit organization that supports HDF5. They are located in Champaign, Illinois, actually, so they're very close to us. There's some folks from HDF Group here today. I recommend you talk to them if you're interested about their product. HDF5, by the way, is open source, and it's got bindings in every language, Python being one of them. The module we use is H5Py. It's very performant. It just wraps some C libraries, so does everything for us that we want. But the challenge we had with operating on the HDF5 files was the way the files are saved is sort of arbitrary. It buffers the data. It saves it maybe every hour. And so when we take slots of data, we might fall on an interval between two files. Or if we ask for a very wide interval, we might grab more than one file. So we wrote a data access layer, which actually abstracts that, and all we do is give it the date range that we want, and it goes off, finds the files that is satisfied by, and reads it into memory. So challenges around using HDF5 are, so you've got all these files, you've got all this data in the files, but if you're running them on a file system, you don't have a way to know what's in the files until you open them, and that can be very costly. So we've had to implement an indexing service that can read some of the metadata and put it in a storage solution that can retrieve that information very quickly. I/O scalability, now that I'm reading on disk these many files, I can only read so much data in one process, so I like to go multi-process. I like to do multi-node if I can, and that's a scalability issue. And then cloud storage, finally, as we go into the cloud, HDF5 is a binary format. It requires POSIX compliance in the file systems, and the cloud storage providers don't have this as of yet, or it's very expensive. So we're trying to find a solution, and the HDF group is working on that as well. So now we've read the data into memory for a given session of data, a 10-minute window. At this point, it's just conventional scientific computing. This is the stuff that we've been doing in Python for years. You just have a data set that's finite, and we need to go compute things that probably couldn't be done in an embarrassingly parallel way, like filter the data in a forwards-backwards way. I have an example of that here. Or do event detection, where we're actually looking through the data to find maybe when something happened, like a gear shift. So there's great libraries for this. We use NumPy, SciPy, especially the signal processing module. And then Pandas makes the things that are Boolean related very easy for doing split, apply, combine type of workflows. So the two examples I show here are, this one's a pure Boolean feature. When channel 1 does not fall in this list of -107, when channel 2 is greater than a threshold, and when channel 3 is greater than 0. So we take all those Booleans, we AND them together, we sum them up, and count how many data points in the window is this true as a percentage of time. The one on the right is a signal processing example. So we have a phaseless exponential averaging filter that smooths the data, and it smooths it in a way that sort of pays more attention to the long trends rather than the short, noisy trends. And we do this in a forward-backwards way. Filth is a forward-backwards filter, so it doesn't induce a phase shift, which is important. So we do that inside of one process, one worker for that window, and we can produce a feature and put it in the feature vector. One thing I'll mention is the CPU bottlenecks were really not thought to be a problem. We were I/O bound, took more time to load the data, but once we scaled this thing out, I found that the naive code I was writing actually was starting to be the bigger part of the process. It was taking about 75% of my time to calculate these features. So I went back and rewrote the feature code, to be more performant and reuse variables. And I found that then I got a good balance. I was maybe spending 1/3 of my time on I/O and 2/3 time on CPU. So distributed computing, now we're talking about how do we scale this up. And we use Celery. Maybe a bit of a strange choice, but I'll say that when we proposed the project, there was the thought that we would make this into a backend for a web application that non-coders could use. They could just fill out a form, click go, and it would go and submit a job and get it back. So Celery is very good for that. It's used in production environments. It's robust, scalable. You just add nodes. You can add and remove. It's very fault tolerant. But it's not super flexible to changing code. It really wants static code when you start your cluster, and that code shouldn't change. So that's been a bit of a challenge to think through. The example on the right here is one that we ran that was only 3 nodes, but you can see we got parallelism. Each node had 4 cores, and we did about 150,000 windows of 10-minute window each. This process would have taken 48 hours on a single process, single node, but because we parallelized it 12x, it took 4 hours. And this process is scalable, so as we go into the cloud, we can add 32 nodes, and the time just shrinks till we get to minutes. So our workflow in general is we have a generator that feeds these window session arguments on what the data needs to be read for each window, and feeds that to the Celery queue. That's sequential. Then Celery asynchronously processes all of our tasks in parallel, and internally, that featureized code I showed you, that's done using a functional programming pipeline, which I'll show you in the next slide. So finally, all those workers send their data back to the driving process. The results are brought in, and we then can do the data science, the filtering out the bad sessions, the vectorizing the data, PCA transforming, clustering, and finally generating the report. So PyTools and SciTools, we do use these to make our life easier inside of a worker. We've got a lot of steps we go through. There's a lot of funny things in the data that can happen. Sensors can drop out. You go back far enough in history, and our schema might have evolved. We may have not had a channel back far enough that we added later. So in this workflow, as I show here, we've got a decorator that basically anytime an error is found, we can not abort it, but pass results that basically says, I don't have any data, I'm empty. And it kind of just flows through the process without kind of breaking the code. And then we string all these together, all of these functions in a PyTools composed way that just basically creates one function that we map against each of the windows. So I highly recommend you look into PyTools if you're trying to build a pipeline of custom functions. PCA transformation, this is the easy part, easy relatively. We've got good libraries for that. Scikit-learn's got a PCA class. We just call that on it. You get the results back, and then you can look at the explained variance ratio, do a cumulative sum, and find that point of which you're right just beyond 80%. K-means clustering. This is another drop-in from the module scikit-learn. You just call k-means and do your fit on it. One challenge I will mention is k-means is really not clustering, even though it's called that. It's partitioning. It takes your data space and it tries to create like sort of equal regions of space in the data. So if you really want true clustering, like based on density, you'll look at a different method. And then of course, choosing an optimal number of clusters, that's sort of an art, not a science. So here's my example results. Let me just orient you to what this is. This is, we pulled out for a given cluster, cluster 1, there's the vertical lines demarcate where the windows begin and end. So there's five sample windows, and these would have come from different machines in different geographic locations, different operators and so forth, but the same machine. So here's cluster 1, and then here's, there's 13 of them. I can't show you all of them because it'd be too small, but here's 4 of them. And your eye can sometimes pick up on what the trend is. Like I see on this top left one, there's a lot more variability in these 2 curves that are in the middle. But sometimes you'll say, well, what is the difference between these 2 sample clusters? And I feel like they look visually the same. Well, it turns out when you look into the details of what features were clustered, there are indeed differences. So for these four, the domain expert kind of reviewed the data and said, well, what I see here is a trend of top one is in high gear and slowing down. Top right is in neutral, it's waiting in a line, it's backing up. The bottom one is mid-gear traveling and doing hard work. And then the final one would be mid-gear and slowing down. So they confirmed that this indeed is finding patterns in the data, at least at a comprehensible level. Here's another example in large mining trucks. I think we found 10 clusters, and I can show 9. Funny thing, we usually do see in the top middle plot there, we usually find a cluster that's idle. I mean, data's flat, all the features are kind of near zero for whatever we're calculating. So you do hope to find that, and you hope that the idle's not spread out in other clusters, or that would be an indication it's not working. Wheel loader, again, there's like top right is sort of the idle state. Some of these you can see visually. This one's got some half activity, half idle. There's some lots of slow moving activity, and then there's a few clusters of high frequency movement. And whatever features they clustered around, they are in fact different. Track type tractor, this one was interesting because at this, I had a lot of channels for this one, a lot of time series plots. I can actually only show you, I think this is about 10 in the first plot. And first when I looked at these, I thought, wow, there's a lot of this stuff actually looks the same. But when you look at the second set of channels in the second plots, and you have to look at the combination of them, right? So they might look the same in one series of plots, they might look different in another, or it's really the joint between all of them that they find the clusters. Really, though, to get the insight of what's different, what I find is we're always going back to this PCA pairwise plot. This is my favorite plot because when you look into this data space, you can find the region that the data is centralized around. One difficulty of this is using Seaborn, I believe. One difficulty is it plots the data in a way where the first clusters are plotted, and then it plots the second set of data, and then the third. So it's the last clusters that are most visible, and the ones that are plotted first. So in this one, it'd be the light blue. It's actually kind of obscured. So what I found, and it's necessary if you're really trying to distinguish two clusters, is just plot those two clusters in the pairwise plot. Then they won't be obscured by other clusters. Another thing you can do is get out of the pairwise domain and look at just the raw principal component values, the distribution as a histogram. Sometimes you'll see like, oh, it's, back up here. You know, it's hit or miss, but you'll say maybe one principal component is definitely at the low end of that for that cluster, and this other cluster is at the high end. So another way is just review the data in this space can help. And then finally, we can go back and look at histograms of the actual features. So this was a feature I grabbed, and you'll notice that like cluster 4, all of the values are way on the high end. Cluster 7, all the values are at the high end. All the other features have a lot of data on the low end of that range for the feature. So, but it's really, I mean, think about it. We're not clustering at the feature level. We're clustering at the principal component level. So you get a mixed bag of whether this is really helpful to look at an individual feature. And then finally, this was what I was saying earlier. This was a data set with smaller principal components needed, only 4. But you see that overlapping problems happening. So what I show here is, okay, plotting just 2, plotting 3 different clusters, and it becomes much more evident, yes, the clusters are separated in the principal component space. And what I've found with our data is it's very globular in the principal component space. It's not spread out. There aren't islands of data for the most part. Here's an exception where like the purple cluster is very much on its own. It's like a peninsula sticking out on the data space. So in conclusion, what worked well and what needs improvement? I'll say that the team has been very impressed. They say we are producing believable patterns, useful patterns, and they can introspect what those cluster identities are using visualization. We found a way to scale the problem up doing parallel computation on Celery, and clean functional programming pipeline that makes rationalizing about the code very easy. What needs improvement? So over time, we had to run this many times. We would find errors in the feature code. For example, when you say when throttle's at 0, call call that a percent of time that you're at 0. Turns out when the guy is at 0 in the cab, the signal might be at 0.01. So we have to go run a whole job and find out that the feature needs a little margin, change the margin, rerun it, and then it improves. So doing that over again and over again, we found that we needed a better workflow management and way to compare results one versus the next iteration. Celery can be a little rigid, as I mentioned. So if I define my features right now and try to run them and the cluster is already running, you'd have to stop the cluster and restart it. Although I found a way to hack it so that you could serialize the function and get it to load that on demand. And then it's a bit quirky. We had a few things go wrong that we changed the code and then it worked. And then the last thing is we might investigate a better clustering method. So k-means is great for partitioning the space, but if we want to actually look at where the density of the data is, we're looking at HDB scan, which is a very good recommended algorithm. And then maybe what multivariate stats are better used for finding that optimal number. Here's my last slide, recognition. And this was a team effort. We had Michael Anderson and the IPS core group giving us their domain expertise. These guys are not coders, but they know what they want out of the data. Code development team, I had Casey Jen and Sanjeev Armagam help me. And the data science, I'm a mechanical engineer background, but I am a developer. So I got my mentoring from Sang Kim. And then finally, we had some guys very good at the distributed computing, Ankur Dadanya and David Vieiro, who are actually here today. So great team effort. We're really happy with the way this worked out. And with that, I'll take questions. Does feature engineering require domain expertise? Yes, it does. Although I think they struggle sometimes on what are the best features to have. And, you know, initially I got a laundry list of features. Like, here's 500 features we want. And I said, well, are all these really unique? So we would work through, you want these specific features out of your data. Maybe we can combine some. Maybe we can make, rather than like count every time a value is different in the channel, maybe find regions of that channel which are actually more functionally important. So yes, it took someone like me, I guess, to kind of talk with them about the mechanical engineering and about their systems, but then be able to translate that to code. So I would say yes. Yep. Say again? Transform-based features? You mean like FFTs? Oh yeah, okay. So like frequency-based methods, spectral-based methods, you see those used a lot when you don't have an idea what you want out of the signal. You're not looking for events that happen, or you're not looking for not waveform features, but maybe like percentage of time that this value is across a threshold. If you just get the data and you're a data scientist, you're not knowledgeable about the data, I would probably go the way of doing spectral methods, because that does tell you things about the wave, like the low frequency trends or the high frequency trends. I'll give an example. There was a Kaggle competition on brainwave data, also time series, and they put that out as a contest. The winner actually used, I think it was like 20 different features, and a lot of them were either signal processing or spectral based. So that's probably what I would do if I didn't know what I was looking for in the data. Thank you. Yes. For prediction, is there anything that we're trying to predict? So this was an unsupervised problem. I was really trying to find structure in the data. But after we've solved that, they have started talking about, okay, does this change over time? Like if I cluster the data today or in this geographic location, do I see data coming in that looks different? And that would be an inversion of the problem. That would be a classification problem. I've got some ideas. You could take the centroids that you get out of this and then classify your incoming observations to see, are the distribution of the counts of those classes staying the same, or is one going up? Are you getting, if you use a density-based method, you could say, am I getting a new region in the data space that's never existed before? So I think that would be a way to make it predictive. Yes? Okay, right. So how long did the project run from start to finish? And second part was, what is it being used for? The value and the practical. Okay. So we started maybe talking 3 years ago, and actually one of the hardest part of the project was really defining the problem. It took about a year to figure out that they really wanted unsupervised classification, because the way they've been doing it was we're finding cycles in the data. It starts at this location geographically in the mine, it goes to this location, and they would pull it out. And so it looked more like a supervised classification problem, but the more we kind of worked on that, we kept being told, no, that's not really what we want. We want you to tell us what the structure of the data is actually looking like. So it took a year to work through just conversations on what they were looking for, and then to devise an actual kind of workflow that would work. Then it took another year to write the first version of code, which was very sloppy, I'll have to say, because we didn't know what things were going to change and what things would need to stay the same. We weren't really building it for scale either. It was sort of a research project. And then in the third year of the project was converting it into like a production model that we can run with robustness and scale it to different features, because it was really tied around the features of the first prototype, right? And then the practical application, back to the very beginning, I talked about software validation. So they are hoping to, I don't think they've quite done this yet, but take those samples and drive their simulation models to show that there's no corner cases or failure modes that they didn't anticipate. So control validation, software validation is one, but they're starting to get these side insights that weren't expected either. So because they're able to see samples of the data and they're told that, hey, there's this many window counts in your data, they can say, oh, in South America, large mining trucks never use the high gear. I didn't know that. I wonder why that is. And then they can go into the data and maybe try to come up with a hypothesis related to that. Other insights are that the data isn't what we want it to be. Like I said about, throttle's not at zero, it's a sort of almost zero. Or that maybe we're not recording some of the channels that we need to for the study. So it's just scalability and visualization of the data has been really big on opening our eyes into what we want to do with the data and what we need to improve. So, thank you. In the back, last question. Sure. So I'll try to repeat. Are we partitioning it to look for, you said maybe by temperature region, geographic, age of the machine, to see if we can find some comparisons that this area is very different than this other area? And I'd say yes, to some extent. We haven't fully explored that area, but the two we were most interested in was geographic location. So are our machines in this area running very differently than this other area? And there's a challenge for that, because you can either cluster them separately and get a good idea on what patterns are unique to one area versus the other, but they're not kind of comparable because of the way k-means works. Or you can cluster them all together, in which case you kind of get a uniform view of what clusters occur on all those locations, and then you can pull out the count per geographic location. Another one they want to do is we release software updates, and they would like to know, with this software update, was the performance of the machine different than after the software update was made? We haven't looked at temperature or climate conditions, soil conditions, but I think that would be in the future as well. They're mostly seeing that they could do by customer, if they had more side data, right? If we could get data on, well, these machines are running in this industry, or these machines are running under this dealer area, are they getting different behaviors based on that? So this enables a huge amount of further study that hasn't been explored. Thank you. Are we done? Thank you.